got that, I think, going out over YouTube, so that's good. Okay. Okay, so we are actually live. Yes. And the mics are hot, okay? So, good evening, everybody. This is Gary Hawkins from the San Diego Astronomy Association. We are having a few technical difficulties as we start out here, which we will hopefully resolve in a couple of seconds. So just stand by, and we will try and get this show up and running as soon as possible. And good evening, Jerry, from Hawaii there. Yep, as you know, some of us, sometimes I like to use the term whack-a-mole, and that's where we're at currently this evening. The SharpCap, our main program that we use for doing our live stacking. I run the beta version, which I've never really had a problem with until this evening. And unfortunately I'm having a problem, so I've had to reinstall the earlier version, and that is throwing things a little bit. But like I said, hopefully we'll get this set up in a few minutes and we'll be able to get going. So just bear with us, and we will keep our fingers crossed and see if we can get this up and running. And that wasn't a good sign. Oh, man. All right. Dave, can I get you to just go round to the other side of the mount and switch the mount on off again, please? Yeah, please. I'm going to have to see if I can. All right. Cycle it on. All right, thanks. And if this doesn't connect this time with this version, I'm going to have to, I'll have to try the other software, I think. All right. And good evening. We've now got 12 on. Jerry, Jeff, great to, thanks for joining us. We are suffering a few technical problems here at the beginning of our live stream. We're just trying to get our computer to talk to the telescope, and unfortunately at the moment we're being somewhat unsuccessful in doing that. So we're just going to try and get this going, so bear with us, and we will try and get this live stream up and going as soon as possible. But the only thing that is working successfully at the moment is that the broadcast software is working, which is great, but it's not very helpful. Dave, you are heavily zoomed in on your camera, so if you, okay, great, all right. All right, let me try. And see if I can get it going this way. Okay. Is the mount on or off at the moment, Dave? It is on. Okay. So for those of you who are not familiar with OBS, we are able to show a variety of different screens, which is why we're showing our standby screen at the moment while I try and resolve whatever issue I've got going on here. Dave, I think what we're going to need to do here to try and at least make some progress is Why don't you start with the introduction,
Okay.
and I will try and continue to juggle with this and find out what the problem is,
Okay.
because I, for the life of me, don't know what it is at the moment. I cannot get EQ mod to talk to my mount at all, which is weird, because this was working. We had all this working. I am not kidding. We had all of this working about 30 minutes ago when it was light, which of course.
And do I have a mic?
Um, is your mic working?
Well, I don't know.
Okay, so now we've lost Dave's mic as well, which is just adding to the. Let's see if we can get your mic going, Dave. Uh, actually, well, that's weird. I'm going to disable your mic and re-enable. You know, I think what happened is we lost. I think our hub went down,
Could be.
and I think it's screwing everything up now. Because I am now not seeing your microphone. Your Oh, there it is. It's just reattached itself. Okay, so let's. Can you? No, that didn't work. Can you give me some audio?
1, 2, 1, 2.
Not working at the moment. Right. Let me try and go into settings again. Um, uh, oh my God. Why is this not working?
What a power cycle the headset.
Okay. Let's see. Dave, can you give me some audio?
1, 2, 1, 2.
Okay. So I've got my I've got I can't read the comments at the moment. Oh, well, somebody's talking about whack-a-mole, so that's good. Yeah, sorry guys, we're just struggling here a minute. Dave's now lost his microphone to add to the problems here. So uh,
Cycle power on this.
yeah, can you cycle the power on that? And I'm gonna try and get the oh dear. Right, deep breath, Gary, because something you've got to work out what's wrong here. Right, let's go to.
Cycle the power.
So the problem that we were having here earlier, which is I think what's actually still causing us issues, is that one of my programs was eating up all the memory here, and consequently.
1, 2. I have a mic back.
Oh, you have your mic back?
Yes.
Oh, fantastic. Okay. So I think we can start with the introduction, Dave. So let me transition the slide across. Why don't you do the introduction and everything, and hopefully by the time that you've done the introduction,
We'll have something
I will
going.
have got the mount working again, because
Okay.
that is critical to the operation at the moment. So like I say, good evening, everybody. This is Gary. I'm going to hand you over to my colleague in crime here, Dave Decker, also from the San Diego Astronomy Association. And we are joined actually by three other colleagues who came out to see how smoothly our operations go and are now all standing around us chuckling because things are not going smoothly at all. Um, so I'm going to hand you over to Dave and let Dave do the introduction while I try and sort this out. And Dave, if you can just say transition the slide. Can you see
Oh.
what slide I'm on?
Yes. When we get to the
Do you want to actually like stand over me so that you can see the
yes,
slide?
I can do that.
Okay,
And
great.
so we'll bypass the first couple targets. Get back to them later.
No, we're just doing the introduction. So the introduction slide. So
Oh, okay.
OakOasis and all of that stuff, right?
Yes.
Okay.
So good evening. This is Dave Decker, and we are at the OakOasis County Preserve. We are very grateful to Ranger Kyle and the County of San Diego for cooperating with us and allowing us to come out and set up here. It is a beautiful site for setting up a telescope. It's reasonably dark. It's close to San Diego, and we have a lot of good friends and resources here. So that's a good thing. Our event tonight, and hopefully we'll be able to proceed here real shortly, in March, is basically a goodbye to winter. Our last, not our last event, but we did an event in December on the winter solstice, and we're saying goodbye to winter at that point. That was the conjunction of Jupiter and Saturn. So now we're saying goodbye to winter and the winter solstice and the great conjunction. And we wanted to get one more last look at those winter objects that will be going away as they're headed west and sinking into the sky until very late this year. So why are those things sinking into the sky? Well, the times they are changing. And for those of you that remember Bob Dylan, you remember that song very well. And I would ask Gary to sing a few bars of that song right now, but he's somewhat busy whacking moles over here with computers and USB problems. So anyway, we'll pass on that right now. But anyway, what happens, of course, is that spaceship Earth is in an orbital path moving around the sun. And as we go around the sun in this somewhat circular path, when we're looking out at the dark sky, we see different scenery. So spaceship Earth has different scenes as we go through the year. And that's what's happening. We're losing the winter scenery and moving towards the spring scenes, the spring objects. So tonight, our objective is to look at some of these objects that are still in the western sky before we lose them until next year. And we're going to delay our first looks until Gary can whack a few more moles. We can solve that problem. And in the meantime, are we going to go to the slide deck?
Yes, I'm on the slide deck now.
Okay.
I am on the slide deck, so I can change to the second slide.
Okay, let me check here.
I cannot believe how much is. Oh, there we. Okay, Dave. We're the second slide is now up.
Okay. Stand by.
Oh, come on.
I'm just enough of a time delay here. Okay. OakOasis?
Yeah.
Okay. So, and we talked a little bit about OakOasis already. This is a county preserve in East County near Lakeside on Wildcat Canyon Road. And it has some great trails out here if you're interested in coming out during the daytime and hiking some nice trails, seeing some great scenery. And right now, as I was driving up tonight, I noticed on Wildcat Canyon Road, there's a great bloom in progress of the ceanothus plants, which is commonly called the local lilac. And it's a beautiful, beautiful color, big, huge, healthy plants, big, huge globs of nice violet, beautiful color coming up. So ceanothus is always something to look forward to in the spring. And
Dave, I'm gonna have to cut you off there for a second because the only way that I can think, I know what the problem is. So I've identified that so before we went on air, just to give everybody an update here, I was running the beta version of SharpCap 4. And usually the beta version works quite well, but unfortunately the latest and greatest version is showing memory resource allocation errors. And so I then had to download SharpCat version 3.2, which I've installed and I've got running on the PC. But unfortunately, I think what's happened is that in order to complete the driver installation,
Yes.
I need to reboot the computer. And as I reboot the computer, I'm going to take the stream down here. Okay, so the only thing I can think to do here at the moment, guys, is I'm going to reboot my computer here, which is of course going to close down the broadcasting software. So if you can all just stand by for a second, give me 2 minutes here, and I'm hoping that when the computer boots back up again, the driver's going to install properly, because if I can't get this driver installed properly, I'm not going to be able to control the mount at all.
Okay.
All right.
Good luck with that, and so maybe hopefully we'll see you back in
Yeah.
a few minutes.
Just apologies, guys, but
Okay.
I'm going to end the stream here. I'm going to be back. There we go. So let's try that. Okay. Hopefully, yes, I believe we at least have a connection again to everybody. We've rebooted our computer here. If somebody could just let me know that they hear us, that would be great. Yeah, you're back. Okay, thanks, Mike. We are having technical problems here, as you might have heard a couple of minutes ago. Dave was just doing the introduction. Talked about let's try that again. You talked about OakOasis, right?
Yes. Yes.
Do you want to talk about just roughly where we are, Wildcat Canyon, and the equipment, right? And then I can just see if I can get this up and running. Of course, Dave doesn't know a huge amount about my equipment, so maybe I should do that. So we're actually under about Bortle 5 or 6 guys here out in OakOasis this evening. I'm using my a slightly upgraded C8. This has now got, I've added a Pegasus power box to it recently, for those of you who are familiar with my setup, and I've also added dew heaters, which have been helping a lot to suppress the dew, obviously, in the winter months. It's running with a focal reducer. I'm using a 553 color one-shot CMOS camera from ZWO, and everything is mounted on a equatorial mount, which is a Skywatcher EQ6R. And the good news is our port has installed, so that's good news. So let me see if I can now fire up SharpCat here. And in fact, if I transition to the next slide, this gives you a full list of hardware and software that I am actually using this evening, running at a focal length of about 1300 millimeters, and my mount's connected, so that's good news. So yeah, I had to reboot the driver there to get going, Dave. So I am now going to I'm just bringing up my software packages in the background here. So and I'm using SharpCat Pro to do the live stacking. I won't dwell on that since we are kind of already a bit late in our program. And we are going to go straight into observing session 1. But Dave, before I go into observing session 1, do you want to just talk about the electromagnetic spectrum a little bit, and I'll just get everything running?
Chat about that now,
okay.
And we can get back to the things. So hopefully, looks like I've got a live mic, and I'd be happy to talk about that. And so I'm going to look over your shoulder so I can see that. So hopefully you see up on the screen a picture of the electromagnetic spectrum. And this is the thing of, it's the way we look at the sky to figure out something about these stars. And we were going to show you some stars leading into this. We'll get back to that here in a few minutes. But in the meantime, let's chat a little bit about the electromagnetic spectrum. So way on the left, we see very long wavelengths, and way on the right, we see very short wavelengths. And it's pretty well documented in that image, and you've probably seen something like this before. Along about in the middle, just to the right of the middle, there's a vertical band of light that uh, is a very narrow section of that electromagnetic spectrum that we call the visual spectrum, or what we can actually see with our eyes. And in the lower half of that screen, the visual spectrum is broken out into its color bands. So on the left-hand side of the visual spectrum, we see red, and on the right-hand side, we see violet. So those are the wavelengths of light within the visual spectrum. And until a couple hundred years ago, the visual spectrum is all that we had to look at the sky. We did not have any tools to examine electromagnetic spectrum outside of the visual bands. So astronomers would look at the sky, they would see colors, they would see intensity, they would see position, and they would do their best to document that in their notes and in their research. And they did a very good job considering what little tools they had. Then, of course, the telescope was invented. We did much better looking at that band visual spectrum of light. And eventually, we applied photographic techniques to the telescope. And the photographic techniques allowed us to expand our capabilities in capturing that light and analyzing it. So that's pretty much the basic visual spectrum of light, and we're going to be talking about that a little bit more. Should we go to slide number 2, next slide?
Sure, here we go.
So here's a slide that we were going to talk about a little later in the program, but we'll talk about it now. And we have 2 images on this slide. One is an image showing a photometric light curve, and the other one is an image showing a spectroscopic light curve.
Sorry about this, guys, but I am being attacked by a bug the size of a cat that has decided that my computer screen is the latest and greatest thing. That this thing is huge.
Yeah, I think he's... There he is. Oh, yeah.
Man, that thing is huge.
I think he's trying to solve your USB problem.
I've solved it. We're good. We're good. We're actually imaging, so we are good here.
Let me finish this slide here.
You finish this slide here, yeah.
About this a little bit. These are 2 different ways of looking at light. If you look at the photometric curve at the top, it talks about how bright light is. And we use the term magnitude, various things. It gets bright, it gets dim. And that's one way that we can look at an object, and it changes brightness with respect to time. If you look at the bottom graph there, that is a spectrum of, and I can't remember which one it was now. Let me see. Anyway, a spectrum that I took a while back, and it represents the spread of the colors of light coming from the star. So I think that looks like Betelgeuse, but I can't read it. So that is what we talk about in spectroscopy. You take the light and you break it out into its color bands and measure the amount of flux or the intensity at each color of light. And we call that a spectrum. So the light coming from the stars gives us intensity, and it gives us a band of colors. And we've learned to analyze the starlight in these 2 fashions, using the total flux in photometrically and the spread of the colors spectrographically. So we were hoping to do something with Betelgeuse on this line. And while we are still getting up and running here, Betelgeuse is a very interesting thing. We will be looking at Betelgeuse here shortly. And starting in about October of 2019, something weird began to happen with Betelgeuse. It started to get very dim. And it dimmed quite fast, quite quickly. And it was so noticeable because even visual observers would compare the brightness of Betelgeuse with the brightness of Rigel. And we all noticed that Betelgeuse was looking dim compared to Rigel. So photometrically and spectroscopically. We recorded all this. Everybody turned their cameras to Betelgeuse and began to try to understand what was going on with this strange behavior. And because Betelgeuse is late in its life, there was always this supposition, well, maybe it's getting ready to go supernova, the big event that we've talked about, which could happen, anytime in the next few thousand years. So is this happening? Well, it turns out through very simple spectroscopic and photometric analysis, we realized that the star got dim photometrically, but it didn't change that much in spectrum. So what we realized is the star itself hasn't changed, but something's come between us and the star, a cloud. So the conclusion right now is that, and the belief right now is that Betelgeuse got dim because of a cloud of some kind of interstellar gas that is interfering with the light between Betelgeuse and Earth. And that's the best guess that we have right now. Of course, it's still being analyzed. But we can tell that because the nature of Betelgeuse didn't really change much. And yet, the overall light output did. So that's why we believe that there was something interfering with that light.
Okay, Dave. I think I am there. I am actually trying to get my first images up now. The good news is the mount is actually talking to the software. Okay, so all right, let me switch on the live stacker here, and so our first so had you finished off that slide, Dave? I'm all over the place
yes,
now. Okay,
I am with that slide, and I'm not sure where you are at this point.
I am on I'm on M43.
Okay.
I'm imaging, and it looks like I am basically up and running here. So I can go to that image if you want me
yes,
to.
That'd be great.
All right, so let me do that. So let's see. All right, let's do. Okay, so let me pin that here. Okay, right. Okay, great. And we at least have our first image up of the evening. So sorry for all of that. 32 minutes into this, and we're still struggling. My focus is possibly a little soft as well, but I think it's not too bad. So we'll see where we go with this at the moment. I'm all over the place. I can't get my thought process here at the moment because this has started off so badly. But what we thought we'd do, as Dave mentioned, is pick up some of the winter targets that are about to disappear into the western skies. If you remember from a few weeks ago, in fact, we've done a couple of presentations now where we've imaged M42 or the Caldwell objects associated with the Orion molecular complex. So we thought we'd start tonight with M43, which is the small circular nebula that sits behind M42. And as you can see, we have that up on the live screen currently. And don't forget to run the camera's cooler. Yes, Frank, I'm good on the cooler. The cooler is running. We've got dew heaters running on the C8 now, so all of that should be solved. So hopefully we will be error-free for the rest of the evening. So I have a fairly decent image of M43, Dave. Do you want to say a few words about it?
We have some notes on M43. We have looked at this complex a few times recently, but I'm not sure that we've highlighted M43, which is a sort of circular, on our screen here, the sort of circular cloud to the left of the trapezium, or the main part of M42. So that circular area is actually identified separately. The Messier gave it M43, and it does have a different NGC number. And it's on the other side of this dark kind of a cloudy thing that separates M42 and M43. So we see a cloud. It's on sort of, on our view here, sort of the bottom side of M43, and it's that big finger that juts into the middle of M42. So that's a cloud of some kind of dust or something that's blocking the light. And it separates the two cloud structures. So we can actually say that it's a different cloud structure. Not sure we've talked about this in the past, but I wanted to make sure we saw this before it disappears, this spring. And that dark, cloudy stream in there, that cloud in there, has been given the funny name of the fish's mouth. And so you will hear someone talking about in astronomy, oh yeah, the fish mouth or the fish's mouth. And what they're talking about is that black, dark area that separates M42 and M43.
So this must be the area, whoops, let's see, this must be the area to the right-hand side of the central star of M43, Dave, is that correct?
Yes, the central star of M43 is called NU Orion, and it's below that, and travels across on the bottom side of that cloud into the finger or the dark cloud that points towards the trapezium.
Okay, so, oh yeah, okay, so I think now I've probably got my mouse showing on the screen here. So this is this area here, right? This is the fish's mouth here. Oh yeah, okay, so you can see the head, right? So here's the jaws, and then you could probably say this is an eye or something.
Like the fish's mouth.
I got it, okay.
That would not have been my description, but it's one that's in the common lexicon, so, we'll go ahead and use that, I guess.
Okay.
So M43 is an area of ionized hydrogen, and it's illuminated by NU Ori, which is a triple star system, actually, and a fairly large main star there. And so the light from that star is illuminating this gas cloud around it, the hydrogen or H2 region around it. And the interesting thing about M43 compared to M42 is that the gas clouds are expanding at different rates. So M43 is expanding because of the ionization or the thermal pressure that NU
Dave,
Ori.
I'm sorry. We've got Cindy was saying that we've got an echo, and I have the feeling. There you go. If you
standing too close.
Yeah, you're probably if you actually want to stand at your screen now.
Yes.
I can get you up on the second video camera.
We're good.
Wow, there we go. Look, we've got an image of the sky and the two of us. You're not quite central in the image yet, Dave. Let's just see if we can get you central. If you can come across to that way, no, wrong way, other way.
There we go.
No, you're not quite there yet. Just come. Can you see yourself on the screen, right? just move your head until it's in the center there. No, you're.
Oh, it's reversed.
Yeah, there you go. There you go.
We're reversed.
All right. Okay. Fantastic. All right, great. So you can see the two of us now. This is incredible. We've actually got all three things working at once. Oh yeah, and yes, Mike, I've got no darks running and no flats yet. So I'll try and sort that out in a minute. I had to completely restart the system, and because I'm running SharpCap 3.2, I've lost the sequencer. So I'm having to do everything manually now.
You have to do it. It's looking pretty good so far. I think we can proceed.
Okay.
Let me finish up on this little bit of stuff on the gas clouds, because it's kind of interesting to me anyway. So the M43 gas cloud is expanding, and it's expanding because of the ionization pressure and the thermal pressure that's exerted by NU Ori, the large star in the center of M43. The difference with M42 is that the stellar wind from the largest star in the trapezium is actually pushing the are causing the expansion of the gases around it. So M42 is expanding about twice as fast as the M43 cloud. And the difference is the strong stellar winds from the C star in the trapezium. The C star is the brightest of the trapezium stars. We've shown the trapezium before here. You may have seen it elsewhere. And so that's a pretty interesting thing. Also, there's a difference in age. The stars in the trapezium are somewhere around, maybe a couple 100,000 years old. And the star in Nu Ori and the cloud surrounding it is very young by comparison. And I've read estimates as low as 20,000 years. So don't quote me on the exact figures there, but there is a difference in age, and the way in which the stars are expanding the cloud is different. And we can tell the difference in the expansion of the clouds by looking at the clouds spectroscopically, because they give us a different shift in the color band. So anyway, we want to bring this to your attention that M42 is much more complex when you look at all of the other pieces in that Orion complex and how they're interacting with each other. So Gary, what's next?
Okay, great. I was just playing with the histograms a little bit here to see if I could bring out some of the detail in the burnt out image, but unfortunately I'm not going to be able to do that at the moment. So Dave, I think most of this is working now. Okay. What's our next target?
How about, let's see, NGC 2158, okay, which is near NGC M35.
2158.
Okay. So NGC 2158, when we get there, is an open cluster. It's an old one, and it's very small compared to the open clusters we ordinarily look at.
Okay, we've slewed onto the target, so I am going to go back into SharpCap. I'm having to do everything manually now because I've got no sequencer. So in fact, what I've done here is I'm gonna actually shorten my exposure time down so that I don't have to keep adjusting that. So the first thing I'm going to do here is I'm going to do a plate solve, and as you guys know who are familiar with my equipment setup, I use the plate solver ASTAP. So we will do a call of that, which has now happened, and hopefully we will. Yep, we're plate solving, so the mount is now just moving. I'm going to go into my live stack, clear my live stack. What was the target name, Dave? NGC?
NGC 2158.
2158. Okay, so I got that. I'm gonna. Okay, great. So looks like I've got my first images coming up here. So I'm going to. It's okay. Nothing is quite.
So I get a little review here while you're getting that tuned in.
Okay.
So 2158, I thought it was interesting because it's right next to M35, and we often miss it. We don't realize that it's in the picture right there. You have to take a close look at it, and it won't show very, very bright here, but it's an amazing open cluster. To review a little bit, the open cluster that we see regarding the M42, M43 complex, those stars are, in the order of, 20 to 100,000, couple 100,000 years old for the most part. So they're very young. Previously, we've shown and discussed the M45 or the Pleiades, which is an open cluster. And that open cluster is on the order of maybe, let's say, 100 million years old. And they've begun to spread out into the universe around the area. And when we did the Caldwell program, we discussed the Hyades, and Sir Patrick Moore, of course, named it Caldwell 41. The Hyades are another open cluster. They're about over 600 million years old, so they're much older. Now we come to the object we're looking at, NGC 2158, which is right next to M35. This open cluster, believe it or not, is on the order of 1 billion years old. So it's much, much older than the Pleiades or the Hyades or the Beehive or any of those kinds of open clusters, and yet it's still a very compact cluster. So it's a strange kind of a cluster. Usually we find that when they get old, they spread out into the universe around them. So this one is different. Did not want you to miss this opportunity to look at a cluster in the winter that is so different from the big ones we're always looking at. The stars apparently are fairly metal poor stars, indicating that they were probably formed earlier. You know, as far not a late generation stars, but earlier generation stars. So lots of interesting questions with NGC 2158. So that was kind of a cool thing to do.
Yeah, and I think one of the interesting things here, Dave, is that I've just blown the center part of the image up here, and I am a little bit out of focus, so apologies for that. We're a tiny bit soft here, but you can see the number of old stars in this cluster very clearly. The orange stars are the much older stars compared to the middle-aged stars, which are appearing white, and then the really younger stars, which are bluey white, of which there are very few. So you can see that this is indeed a very old cluster just by the star color, and it actually does show pretty well in this image, albeit it's slightly out of focus, but at the moment I've got no simple way of, unfortunately I don't run an autofocuser on my SCT. Everything is done manually, so I can't do much about that at the moment. But we have a fairly nice image of that, Dave, that's come up, and we've only done, let's have a look.
Now we were talking about Betelgeuse. We should probably show that, even though it's a single star.
Sure.
It doesn't show a lot of fancy detail on the screen, but the color, of course, is interesting.
All right, so let's go look for Betelgeuse. So I'm going to go into my star map again. Dave, what's the? I'm going to need to beat cell. How do I spell it? My brain is fried, people.
Try Alpha Ori.
Oh, Alpha. Alpha.
And I'll check to make sure.
Thanks. That would be good. Alpha Ori? Oh, yes. ORI, right? Okay, I got it. So I'm there. So I am slewing onto my target. As you can see, my white box is moving here onto Betelgeuse. So let me go into SharpCap. And I don't probably need to run the stack here, so I'm going to switch the live stacker off. Okay, and I am going to, oh, there we go. Let me see if I'll reduce the, I'm running at a pretty high gain here, so I'm going to bring that down. Oh, actually, let's see. Kind of liked it with the higher gain there. There we go. I think I am okay with that target, Dave. We've got a nice image of Betelgeuse there. I'm shooting at a pretty high gain, so the background's a little, but the color is showing beautifully.
Yes,
really beautiful
the color is the important thing.
Right.
When we talked a little bit about spectroscopy, you saw that on the left end of the visual spectrum, on that particular view of the EM spectrum, the left end was the red end of the spectrum, and it's a longer wavelength, and it means that the star is a cooler temperature. So we measure the temperature of the star by looking at the light, the spectrum of the light that comes from the photosphere of the star. The photosphere is that surface of the star that generates the light. For example, in the sun, the photosphere is what illuminates Earth with light. And that's what we actually see when we're looking in the visual spectrum. So the temperature of the photosphere can be determined spectroscopically by looking at its color. And I won't go through the process here, but we would like to do that someday, maybe in one of these programs, actually run through some photometric or spectroscopic analysis just to show you basically how that gets done. But the curve of the star tells us its basic temperature at the level of the photosphere. And as I said before, when it got dim, everyone was concerned what's going on. And I actually took a spectrum of Betelgeuse over a period of a couple of months, and the basic curve, which tells us the temperature of the star, did not change. So at my very low resolution, I could see that there was not any major changes in the temperature of the star. Yet photometrically, when you look at it the way Gary does with photometry, it got much dimmer. And I think it lost, probably at least half of its brightness. And so it's very striking how much luminance it lost. So that's why the NASA papers that I've read, some of the papers I've read regarding this indicate that the conclusion is that the star was obscured by a cloud of gas similar to that dark nebula that we saw between M42 and M43. So that kind of a dark gas, dust, whatever you want to call it, certainly has the capability of interfering with that light path. So anyway, that's what I wanted to show with Betelgeuse. And
we actually have even though this is a single star, right, it's actually quite a pretty image. And thank you, Ross, for pointing out I didn't have my darks there. You missed the fun part of the show here, where everything went wrong at the beginning. It's probably the worst start we've had to an EAA live session so far. My main, I had to completely reload a new version of my imaging software for reasons that I won't explain. And because of that, I've lost my sequencer, and without the sequencer, my darks and flats are not loading automatically, and so forth and so on. But anyway, I will make a few shout outs here. Jeff, nice to see you. Ross, Cindy, Frank over there on the East Coast. Jeff, Mike, Jerry up in Death Valley, and I'm not sure, Mike, are you planning to do some imaging a little later this evening, or maybe you're doing some imaging and listening to us at the same time? And I will say, Dave mentioned the color of Betelgeuse, and he also mentioned that I've been heavily into photometry recently, which is kind of my current thing that I've been working on. And photometry is interesting because you image in typically, well, you image in multiple bands, but typically the three bands that you definitely want to image in are red, blue, and green. And if you actually take the green color magnitude, if you take the green color magnitude and take away R, which is the red, or you take the blue color magnitude and you take away green from that, you will end up with what's called a color index, and the color index maps directly back to the color of the star. So if I was actually doing photometry now, I would image this, I would collect my images in 3 different color bands, I would work out my color index, and then it's simply a matter of looking that up on a lookup table to see the temperature of the star, and you can actually work that number out fairly precisely. It's one of the many things that you can do with the sort of photometric measurements that I've been playing around with recently. So Dave, I think what would be a really nice contrast, since we've shown Betelgeuse here, is to show a star with a different color equally as bright. So where are we going? Where could we go?
We could do a couple things. I was thinking about going to Castor.
Okay.
It's a double star,
okay.
And there's some interesting history with Castor.
Okay.
So it's not terribly different in color, but they have some different brightnesses.
All right.
And you probably need to have some kind of a number for that, don't you?
Well, first of all, I'll try typing in caster and just see what happens. And nothing happened in my sky map, so I'm
So
going to need
caster is Alpha Geminorum, Gemini.
alpha. So GEM.
Yes.
Okay, I got alpha gem here on the sky map. So
Okay.
I'm going to slew the telescope. You can see my telescope is now slewing back across the screen. I'm going to go back into sharp cap, and my star has appeared. Now, to see the double star, Dave, I may need to bring down. Oh no. Okay, so we've. Here we go. Here we go. Right. So yeah, actually, the color I can tell immediately. The color is going to show nicely different.
Oh, good.
Right. Okay. And I'm assuming that it's the companion to the right-hand side here. That is the. Can you see that on the screen?
I can see it. It's hard to
Hard
tell.
to say. Okay.
From just the picture, it'd be hard to tell. But I know visually when you look at it in a telescope, it's a nice double star. It looks like headlights in the sky. One is a brighter headlight than the other. They're similar in colors. It's just a nice, bright, pretty much white color. And the actual colors, so it's a type A main sequence star, 9400 Kelvin degrees, so it's a fairly bright star, very bright star. And the interesting thing historically about Castor is that as early as about 1678, Giovanni Cassini, well, Cassini, you know that name, the Cassini division in the Saturn's rings, the Cassini spacecraft. He's an important historical figure from the 17th century. In his notes, he documented that Castor was a double star. And that was sort of unusual because others had not done that and at that time. And of course, I don't know if he was using what kind of optical aids he was using. He certainly could have had and probably did have telescopes available to him. I just don't know what he used. But he did document that Cassini was a double star. So later on, with better instrumentation, we discovered and proved that it actually is a double star. And so, as a matter of fact, we now believe that Castor is at least a multi-star with maybe 6 components in a complex gravitational dance. And so that's a pretty interesting thing. But Cassini's documentation of Castor as being a double star is actually the first record of a visual double star or a binary star. So we talk about binary stars quite often today because we have the science able to determine what they are. And yet Castor, one of the brightest stars in the sky, we did not realize, at least I did not realize until recently, that it was recognized as a double star as early as 1678. So that was the interesting historical aspect of Castor.
Okay. Sorry, I'm just typing as well at the same time. Sorry about that, Jerry. I meant to type 553 MC, and I got that completely wrong. Since I've actually got the mic back again, I'll actually talk to that point as opposed to try and type, because I'm not sure I can even read what I tried typing there. So to answer your question, Jerry, I am using a color CMOS camera for photometry. I am actually in the process of writing a paper at the moment that hopefully will get submitted for review by the AAVSO shortly. We'll see. Certainly proved to be some pretty interesting results so far. And I've been calculating color indexes and relative magnitudes and so forth and so on, and documenting those, and it's been an interesting an interesting couple of weeks while we've been looking at some of the standard AVSO defined star fields. Anyway, back to the show. So,
So I'm thinking maybe one more binary star that shows good color.
Okay.
And that would be Almach.
All right.
And that would be gamma 1, say gamma Andromeda.
Okay. Sorry, I'm just trying to keep in. Right. So, give me a target name, Dave.
Gamma Andromeda.
Oh, gamma.
Gamma and. Just A and D should get it in Cartesian seal.
That didn't work. Oh, AND, of course.
AND.
Oh, that's really low, Dave.
Oh, is it?
Yeah, it's right down on my
How come you delayed the show so that it got so low in the sky?
I have no idea, but it's really low, Dave.
Well, if it's too low, then we've lost it already. I guess we'll wait till next year on Gamma Andromeda, which is Almach. For those of you that don't know, Almach is a beautiful yellow and light blue pair of stars, and it makes a great visual target when you're looking at it in a telescope. And so that'd be kind of fun to do. But maybe next year we'll do that.
But not tonight, Dave.
But not tonight. So let me see what we've missed. Let's see, light curve dimming, Betelgeuse spectrum dimming. We're sort of upside down in our program at this point.
Did you want to go to, did you want to do the flaming star or no, not the flaming star, the...
So we could do that. Let me see. I'm not sure if the
have we got upside down in our program?
Yeah. I mean, I'm seeing what we're missing here.
I mean,
supernova types. Okay. Yeah. Oh boy. There's an awful lot that.
Pick a target, Davis. I'm randomly going to shoot the telescope somewhere in the sky.
Well, if it takes you half an hour to find something, I can talk that long.
Yeah, no, I know actually, you can talk that long, but I'm sure our current audience of 20 viewers will shrink rapidly if we go too far on that one. So I just need a new target.
The flaming star would actually be a good one to go to.
Okay.
It'll take a little bit longer to image probably because it's pretty dim.
Okay.
It's an IC 405.
Okay, IC 405. That's what I wanted. Okay, brilliant. Okay. So, okay, I'm not too far away from that. Let me slew onto IC 405. Yeah, thanks for the suggestion of M78. We could certainly do that in a few moments. So I'm on my target. I'm going to go to sharp cap. I am going to plate solve this, so just bear with me a second while I do a plate solve. So I've increased my gain. I'm running on about a 10-second exposure. I may actually have to, you know what I might do here? Once I've plate solved this, let's plate solve first. Oh, well, actually, we're pretty much in the right place. So let's see how this image is at 10 seconds, Dave, and then if this doesn't work, I'll switch my guide package on and go for a longer exposure, because I know IC 405 can be a little tricky to target at times. Right. Okay, so I need to probably reduce that gain a little bit. Okay, I need to turn on my live stacker. I need to clear it. IC 405. Okay, let's see what happens with this. Okay.
So the interesting thing about the flaming star, IC 405, is that there's a strong belief that the star AE Aurigae, which is associated with this nebula, was actually an escapee from the Orion Nebula, only maybe less than 3 million years ago. And so that's pretty amazing to think that this star, which is quite a ways now from the Orion Nebula from our perspective, only 3 million years ago may have been part of that Orion Nebula cloud complex. And so this is pretty cool. And if we can get the nebula to show, I know I've had some issues trying to get it to show, photographing it from La Mesa, but maybe Gary can do something here. It is kind of a cool thing to take a look at.
Yeah, I'm gonna try here, Dave. I don't think I'm gonna get it to image at 10 seconds, so I've actually switched on my PhD2 guiding system, and I've now got the guider working. I'm just gonna see if this will settle down, which it looks like it probably is. That looks promising. So I am now then going to take my exposure time up to 60 seconds. I'm going to reset my stack. And we'll see if we can get something to happen there. So just bear with us while we capture the first image, and I will go from. Hopefully we'll get that. Right, we've got our. Yeah, it's kind of, it's like everything is not just, it's just been one of those evenings, right? That my video boxes keep moving around. The little boxes with me and you in, they keep moving around on the screen. It's like, I'm like chasing them around all night. It's crazy. But the first image is coming in. We're about 20 seconds away. And right, Ross, I hope you're still awake there and drinking plenty of coffee. Ross is the runs the Bolton Astronomy Association in the UK as a good friend of mine. We've known each other for 40 odd years. He's also a very avid astronomer, and I'll give him a shout out because he imaged his 100th comet last night. From Bolton,
which 100th comet?
100th comet. Yes. Wow. Very cool.
Very good.
And he sent me pictures this morning of it. In fact, it might have been the night before, actually.
Oh, ISS.
So yeah, shout out to Ross there for imaging his 100th comet. And yeah, the 60-second exposures here are helping. We're going to need to collect a little bit of image, but I can see some of the nebulosity here.
So are you using the plate solver at this point?
I plate solved to make sure we were on the target, yes.
Okay, so while that's imaging, let me explain a little bit to our audience here about the plate solver.
Oh, sure.
So Gary's using a tool tonight that was actually developed by Jerry Ryan, who plays the infamous 7 of 9 in the Star Trek Voyager series. And any of you Trekkies know that the 7 of 9 worked in the astrometrics lab. Well, the plate solver is a tool that does astrometric resolution of the locations of objects in the sky. And so, you know, we can give her credit for creating that technology in the astrometrics lab aboard the Voyager spacecraft in the 24th century. So, so her job was to figure out where they were in the galaxy and to navigate a way home. So it just dawned on me as I'm talking about this, Gary, maybe that's not correct because we're in the 21st century, and so 7 of 9 hasn't created the astrometrics lab yet. So I guess I have to stand corrected, right?
Well, I personally thought I was just hearing things when you said that, and I was like, obviously Dave's been smoking too much of something this evening because I have no idea where he's going with this particular story and Star Trek and stuff. But yes, so I guess you are indeed correct. We are clearly using a tool.
I apologize, Gary. You know, you're doing a good job in the 21st century with the tools we have here.
And I will say, and this one is actually this plate solver, or it certainly, well, I'd say this plate solver ASTAP is developed by a Dutch guy, and it is by without doubt the fastest plate solver there is
Yes.
out there. It's an incredible tool.
Yeah.
You can plate solve at about an image out every half a second. And if you've used the online plate solver that most of us are familiar with, or one of the other plate solvers out there, you will know that half a second is extremely quick for to achieve plate solving. So it's a great tool. And if you're not using it, I would definitely recommend taking a look at ASTAP.
So the interesting thing happened with me about a week ago. I was using ASTAP plate solver, and I told it to go to Betelgeuse, and Betelgeuse was off center, and I told the plate solver to resolve the plate, and it left Betelgeuse down on the corner of my screen. And I'm thinking, well, that's kind of weird, because all night long it's been putting the object right in the center of my image, and all of a sudden Betelgeuse is down in the corner. So I started thinking about that, and I'm thinking about some of the questions that we have had regarding these programs, regarding catalogs, and how they're used, the history of catalogs, and so forth. What I realized is that the other night I was using two different databases to locate objects in the sky. I was using CPWI, a program that is a Celestron product, and clicking on things in the sky and sending that to the mount to direct the mount. And I was also using the SIMBAD database to locate objects by right ascension declination, sending those coordinates to the mount. And I was using them back and forth and so forth. And what I realized is if I use the SIMBAD database, the plate solver put the object in the center of the image. And yet when I clicked on CPWI and plate solved it, the wrong coordinates were sent. I will say wrong. Coordinates were sent by way of the plate solver to put Betelgeuse in the wrong place. This correlates with a lot of questions that I've had from people contacting me, actually after some of these programs where we talked about different catalogs. We've talked about the Messier catalog, and we've been through that. We've talked about Robert Burnham and his cataloging of objects in the 60s and 70s. We've talked a little bit about the Herschel catalog, the development of NGC catalogs. We talked about the Caldwell catalog, Sir Patrick Moore, who put that stuff together. These are all catalogs, and they help us find things in the sky by giving us right ascension and declination. But there's a complication. There's a real problem here. Sometimes the catalogs from different eras and from different sources show different right ascension and declination for the same object. And originally I thought this was just errors in the way that they calculated those coordinates. But I've since realized that there's a problem with the era because of a thing called the precession of Earth. So the problem is that the Earth wobbles like a top. And as it's wobbling, the North Pole is pointing to different parts of the sky. And it causes a problem because at different eras, different times, especially if you're 25, 50, 100 years apart, your coordinate system gets sort of warped, and your coordinates are correct, but they're not correct for all time. And so I began to realize that that was what was happening. I was using different coordinate systems from different sources to guide my camera. Well, the reason I wanted to bring this up is because we originally wanted to do this show a couple of weeks ago, right about the spring equinox. And the spring equinox is important. It's very important astronomically to the history of astronomy. And because the spring equinox is defined as the point in the sky when the sun crosses the celestial equator going from the south to the north. That happens on the vernal equinox. And the vernal equinox is designated as that point in the sky when the sun crosses the equatorial, the celestial equator. But you see, the Earth wobbles like a top, so the equator also wobbles around. And so at different years, especially if you go, a couple of decades away, the vernal equinox is actually dragged along with it, and with that, it drags along the right ascension declination coordinates, particularly the right ascension coordinates, because that point, the vernal equinox, is considered the 0 point in the sky for right ascension. We calculate in hours around the Earth from that point at the vernal equinox. So if the vernal equinox moves, so does the coordinate system. And it doesn't move just a little bit, it moves a lot. It moves on the order of 50 seconds of arc per year. That's almost 1 minute of arc per year. And you start adding that up over decades or a century, your right ascension coordinate system has changed a lot. So that was one good reason why we're having problems using these plate solvers, because they're based on different coordinates. And this helps us to explain why different eras and different catalogs created by astronomers did not necessarily correlate very well on their location in the sky.
Now, the good thing though, David, or at least what makes this problem resolvable, is the fact that you will notice that the RA and DEC coordinates are given with a time, a year. So the current, and these I believe are updated every 50 years, correct?
Well, glad you asked, because I have a whole lot more to talk about on that regard.
You know, I was kind of afraid you did, but that's fine. I was just going to say before everybody.
Let's talk about the flame.
Well, why don't we? Yes. So we can talk about the flame. We've certainly got it imaged as best as I can. Let me just give any of you that are using CDC a tip here, and you do find that you end up not quite positioning where you expect. Make sure that when you go into your telescope connect settings, which are here, go into the advanced settings and make sure that you are forcing your, well, in my case, I have to force my coordinate system to J2000. So my RA and DEC are forced to the year 2000, even though obviously we're in 2021, so that's 20 years ago. And I make sure that all of my programs are running on J2000 epoch. So that way, everything when it connects together is talking the same RA and DEC. Otherwise, things get really confusing. And for those of you that were on a live stream I did from the house probably about 4 or 5 months ago, you actually saw this confusion take place, because all night I was literally 0.2 of a degree off in my pointing.
Right.
And this was the problem, that my RA and DEC, my epoch was set incorrectly in this particular setting. So, Dave, Flaming Star Nebula, which we have got probably as good as images we're going to get in probably, we got about 12 minutes of imaging. It's a little noisy, but you can see the nebula. You
Sure.
can certainly see the shape quite nicely.
Why don't you, let's see, we have a choice here. We could go to Caldwell 25, the Intergalactic Wanderer.
Oh, yeah, okay.
Why don't you work on that,
okay.
And let me finish up here on this this catalog thing, because there's some very interesting things that the folks need to know.
I will let you say a few more words then, Dave.
So the Intergalactic Wanderer would be NGC 2419.
Oh, okay. NGC
2419.
All right. Well, I will go and sort that out. You finish off the stuff on catalogs.
So back to a little history here. This whole thing about the vernal equinox is very interesting. In the 2nd century BC, Hipparchus observed the sun crossing the equator, and it was in the constellation of Aries. So Hipparchus called that point in the sky the first point of Aries. It's a pretty common term. You may hear that now and then, the first point of Aries. And he considered that to be the place to start measuring locations of things in the sky. And so because of the precession or the wobble of Earth, that vernal equinox, which at the time of Hipparchus was the first point of Aries, is moving west at the rate of 50 seconds of arc each year. So it's moving quite a bit. And what happens is it's moving out of Aries into other constellations. And as it's moving through the sky, it's dragging the whole right ascension coordinate system with it. So it's warping it. And we have to keep making these corrections like Gary just referred to. If you get the wrong year, the wrong correction, then those right ascension coordinates don't necessarily match up. So where is it going to be? Well, guess where the vernal equinox is headed? It's headed to a place in Aquarius. So that reminded me of the song, the Fifth Dimension song, The Dawning of the Age of Aquarius, and now I begin to understand what the musical Hair was all about. So, Gary, do you know that tune?
The Age of Aquarius?
The Dawning of the Age of Aquarius?
You know,
from the musical Hair?
I am a little bit long in the tooth, mate, but I'm not sure I'm quite that long in the tooth. But yes, I am aware of the song with that name.
So the dawning of the age of Aquarius could be anywhere from now until the year, I don't know, 2050 or, I don't know, 2500
It's a 60s song, right?
So the point is that...
Dave is showing his age to everybody out there, but that's fine. Carry on, Dave. Sorry.
The point is that the coordinate system is changing. So to finish up this little bit here, the International Astronomical Union has come to the rescue, and they've created a new coordinate system, and they call that the International Celestial Reference System, or ICRS. And the ICRS has nothing to do with the vernal equinox, because they don't really care about Earth, since the vernal equinox has to do with places in the sky from our reference point on Earth, and it assumes that Earth is the center of everything. Well, of course, we know we're not. And so the ICRS system does not use that. It uses the barycenter of the solar system, or essentially, which is near the center of the sun, and uses that as a point of reference to identify things in the sky. So the ICRS system was implemented after the Hipparchus satellite project, and they remapped the sky based on this new coordinate system. And since about the year 2000 or so, the ICRS system is actually the official coordinate system for the sky, not a coordinate system based on the vernal equinox, which is drug around at 50 seconds of arc per year. So anyway, that's the last little bit here. We now have a coordinate system based on the solar system, and I imagine that 100 years from now we'll have a coordinate system based on the center of the galaxy rather than the coordinate system. And then perhaps 7 of 9's astrometrics will be much more valid.
Well, that was a shaggy dog story, folks.
Oh, you asked for it, Gary.
I certainly got it. So yeah, but it is actually a really interesting thing that you do. And actually, Dave mentioned something else that's interesting there. So you have multiple time coordinate systems as well, and again, the more you kind of get into the science of this, and I've been doing a little bit with some of this stuff recently, is you've got your UTC reference time, you've got your Julian date reference time, you've got your baryocentric time, you've got your heliocentric time. They're all different time standards, and certainly when you're submitting results, let's say for photometry results to the AA VSO, they require Well, ideally you should do it in either barometric or heliocentric time. And I'm not even going to try and describe the difference between barometric and heliocentric because, frankly, I'm not sure I can. But I know that it's generally associated with where the center of the time reference is. So whether it's the Earth or the Sun or the gravitational point of balance between the two, which I think is probably heliocentric time, but I may don't quote me on that. But yes, so we've got the Intergalactic Wanderer, Dave.
Yes.
It's a relatively small globular cluster. I'm actually zoomed in at about 50% at the moment. It's not showing brilliantly. I've got quite a bit of noise still in the background here. I'll try and get rid of a little bit, but we do have the Intergalactic. And why is it called the Intergalactic Wanderer, Dave?
Well, the Caldwell 25, this globular cluster, is about 300,000 light years from here.
Oh wow, way outside of
outside the galaxy. Well, way outside our traditional galaxy. Our galaxy is about 120,000 light years across, and if this globular cluster is 300,000 light years from us, then it certainly is beyond the limits of what we normally consider the edges of our galaxy. It may still be in orbit around the galaxy, and if it is, it has an extremely lengthy orbit on the order, billions of years probably. But this is something that I've missed a lot. This is right next to M35, as I recall. And we look at these large open clusters a lot and not think about it. And here right next to it is this tiny little blob of light that I have not looked for, and we're going to be losing it here as spring moves on. I want to bring this to your attention because here is a globular cluster that is farther away, much farther away than the Magellanic Clouds. And it's outside the scope of our regular Milky Way galaxy. And yet here we are, we're able to see it and image it here and thinking about this. I don't know too much of the actual science about the cluster, but obviously it's given the name Intergalactic Wanderer because
it wanders, I presume.
Not being closely bound to the center of the Milky Way, we don't really know what it is or where it came from. Whether it's the remnant of another galaxy that's been stripped off, I don't know. But keep that in mind, that there's all these nice little weird things that look so dim, and then you realize how interesting that we find this thing that, is so far away.
Yeah, and you can certainly see from the image that the stars are not resolving, and that's possibly because I don't have my calibration frames quite right either because of everything that's happened this evening, and I was a little bit out of focus as well, so none of this is helping. But you can certainly see, actually it's kind of what most visual observers see of DSOs, a kind of fuzzy spot here, which is this globular cluster, which is outside of our own Milky Way. So that's come up as good as it's going to come up, Dave. So let's move on to another target.
I'm thinking the Edge on Galaxy that we did, the Caldwell object, the C23, or it's NGC 891.
Okay. NGC 891. Wow, that is. Are you sure?
Oh, is it getting too low?
It's way low on my horizon.
Oh,
yeah.
That's really too bad. Well, how about M1?
Oh, how about, actually we had a request earlier on for M78, so let me just see if M78 is, I think I could get to M78. Can I just pop over there for a second?
Sure.
All right, so I'm going to slew, because we had a request for M78, I'm going to slew over to M78. It is pretty low on my horizon, but we should be able to get it.
I've had lots of trouble imaging M78.
Oh, really?
Yeah, it's just a difficult one, I think, compared to a lot of other small nebulas like that.
All right. Well, let's see what happens.
But
let me try and reset everything here, and see if I can Oh, that's interesting. The plate solver didn't actually. I wonder. Actually, my mount probably hadn't settled. So that is one of the things that yeah. Okay. I think we're actually there anyway. But let me just run a quick plate solve. Um, that is one of the interesting things that, or one of the things with the EQ 6R mount that I have that I wouldn't say it's not so great, but it's certainly one of the things you have to account for. It does take a little while to settle. And so consequently, if I plate solve too quickly and the mount hasn't settled, the plate solve fails, as it's trying to do at the moment. Which is interesting because it should have settled by now, but I can see the target there, so I'm not going to plate solve again. All right, let me just get set up. Let's just do it on 20 seconds. Let's switch the guider. Oh man, what's happened here? Now my guider stopped working. It's just one of those days today, isn't it? All right. Oh, okay, let me. Wow. So for those who are, you can obviously see on the screen at the moment that my guider screen has gone bright white for some apparent reason. So let me switch that off a minute and I'll try the guider again in a second. Let me just bring this down to about 15 seconds, then I'll reset the stack. Okay, so I'm on M78. So yeah, we'll pick up a few images here just stacked at 15 seconds and see where we go. Okay, I've got my target, so that's good. Actually, we were kind of lucky with the weather today. We've had a really bad run of clouds in San Diego now for the last probably month, right, Dave?
Yeah, yeah.
We've had most nights we've had clouds roll in, so we were kind of a bit worried. We had to reschedule this event from last week due to the fact the weather forecast was pretty poor. But tonight we seem to have got away with it. We did have a little bit of high-level cloud earlier in the evening, which may or may not be contributing to a little bit of softness on the image as well. I can't really determine if there's cloud up there. If it is, it's pretty wispy. And the temperature's beginning to drop out here now. It's getting a little bit chilly. Little bit.
The heater's still working.
Yeah, I don't think I'm close enough to the heater to benefit from it at the moment. But anyway, let me transition across there. Okay. Yep. So I'm getting an image here, Dave. I'll try and clean it up while you talk about it. Oh, you weren't really prepared to talk about it, were you?
I don't have a lot of notes on M78.
Nothing like catching.
I know I've looked at this before. It's an interesting, really large dark cloud surrounding you know, a area of luminance. So it looks almost like an arch or going underneath a bridge or something. It's kind of a cool look. I've never been able to quite get this look when I imaged it a few times. I can see some color and some shapes, but it's kind of cool. It's part of the Orion complex again, and like I say, I haven't done a lot of background on M78, but I have seen it a few times.
Yeah, and I think the sky conditions tonight, Dave, and the fact that we're using such short subs, although I will try and get the guider on it, is going to make this perhaps a tad challenging. You can, I mean, I can make it out on the screen here. So here is the dark area around here. You can see there's a lot. Well, there's a little extra darkness in this general area. If I could get the noise to reduce a little bit, we will actually perhaps get a little bit more definition on that.
I see that Jerry Hilborn has some good notes about M78. Thanks, Jerry, and I hope you guys are reading the chat. Get some good information there regarding M78.
It takes some stacking to bring out the contrast. Yeah, and unfortunately, at the moment, well, we'll give it a little bit of time here. It's only actually stacked 120 seconds, so let's just see what we can get in a couple of minutes. But you can certainly, I mean, I can certainly make out the circular donut-shaped dark area here. It's much more pronounced on the side closest to 2 stars here and here than it is on the other side. But this is basically the donut area right in here where you've got this dark matter around this central nebula. The blockage is between the star endpoints. The blockage is between the star endpoints. Can you clarify that for me, Jerry?
What was that?
It's not on, oh, it's not on the other side. Okay. Oh, then I'm mistaken.
Half
It's
circle,
a
yeah.
half circle. Okay, it's a half circle between the star endpoints.
What did I do with that?
Okay. All right. I'm not really familiar then enough with this target. I can actually, let me just see if I can bring up an image that I shot earlier of this target. Now, when I say earlier, I mean in darker skies under different conditions. I actually keep a database of all my decent shots, or at least semi-decent ones. So that is about the best image I have of M78 to date. I don't think I am. Oh, whoops! I need to. Sorry, guys. I need to transition to a different. Not that one. There we go. There you go. So that's probably the best image I have of M78 to date. It's not a great image, and I don't think I'm going to do any better than that this evening. So let us continue with our scheduled program.
Why don't we try M46?
Okay.
A open cluster that contains a planetary nebula.
Oh, okay, cool. Oh, M46. All right, so I'm going to be slewing towards the south. All right, so I'm on M46. And well, interestingly enough, something else that I've noted here is that once you've plate solved a couple of times, it must be storing the coordinates within the database of the tracking software for the mount, because usually once you've plate solved a few times, you don't need to keep plate solving repeatedly, because the accuracy just is sufficient that you generally end up on your target. Of course, having said that, I'll completely miss this next target. But that was M46?
M46.
Okay.
M46 is an open cluster, and
in
the view of M46, we also see a planetary nebula, which has its own NGC number. But as I recall, a little bit of reading, there's good reason to believe that the planetary nebula is not actually part of the open cluster. It's probably closer to us than the cluster is, having to do with the type of stars that are in the cluster and whether the gravitational effect of the cluster would actually, contain that nebula. So I don't know all the details on it, but from a visual perspective, it's kind of cool to see an open cluster. And on the edge of this open cluster is an actual planetary nebula with, and if we're lucky, we might be able to get some color in the nebula.
Yeah, I'm pretty sure I can see the planetary nebula. So I think what I'm gonna do here is let's close this down. Yep, I can see it. So let's close this down and make it a little bigger. Let me just do this transition as well. And I'm just going to zoom in a little bit here. Okay, cool. There we go.
In
Oh,
my Cliff's Notes version about the planetary nebula, clearly the planetary nebula is something like the remnants of what our sun would be at the end of its life. And planetary nebulas are the result of relatively small stars, small to medium-sized stars, not large stars. Smaller stars last much longer. They burn their helium, their hydrogen shell much more slowly. And so the M46 open cluster is really a much younger cluster than the probable age of the planetary nebula. So planetary nebula should be, you know, like our sun at that stage of life. It's going to be, you know, a billion years old or something, and the open cluster stars are probably much younger, probably half of that. So without doing any more real careful analysis, the planetary nebula is probably this side between us and the open cluster.
and I think, you know, if we look at this open cluster compared to the cluster that we looked at initially, we can see this is a much younger set of stars. The majority of the stars in this cluster are white, so much hotter, and these will typically be much younger stars. And we can actually see the planetary nebula here on the edge. And I don't think I've ever imaged this before, Dave. So I'm gonna collect just a few images here and actually save this one. But you can see the planetary nebula right in here. I can zoom in a little bit. We don't have a great image again, just simply because I am running relatively short exposures tonight, and generally this system images a little better with longer exposures, but with everything that's happened this evening, we just need to just take what we can get, so to speak. But you can quite clearly see the circular nature of the planetary nebula. And actually, Dave, this kind of looks interesting. Do we know if there's the... Because there's actually two stars in this planetary nebula. Is one of the stars not associated? Do we know anything about that?
I don't know anything about it, but I
Okay.
wouldn't think that there would be two stars in the nebula. There could be a white dwarf at the center of a planetary nebula, and it's possible that we could see that. I would say it's more likely that we're seeing a background star through the nebula.
Right.
But you know, without further research, I'm sure somebody knows. I haven't done that kind of research on that object, but
Okay.
due to the difference in ages, you know, it seems logical that the planetary nebula is not part of the open cluster.
Right.
And so, and the difference is probably a difference in distance, calculated distance. And so we're probably looking through the nebula at one of the stars in the cluster.
Okay. I think we've got a reasonably decent image of it. This actually does show quite nicely. You can certainly... It is quite a nice open cluster, and certainly the planetary nebula is nice and visible here. So I'm actually going to save this stack, so I've at least got a record of it, and I might just do a quick couple of adjustments. Oh, I've got way too much noise. Yeah, you can, and so if I go to here, I think this kind of illustrates the fact that my dark frames are not actually calibrated with the way I'm shooting here. You can see this line noise all the way across my image here, so we are kind of struggling with a few of the technical things this evening, but I can, by adjusting the histogram, I can obviously make that go away, albeit that I'm losing some of the detail in the image. But let me just see what that looks like. Yeah, it's not too bad. Let me save that as well. At least I got a record, which I can put in my target database pictures, and go from there. Just trying to check yeah, there we go. The name is M46. Okay, so we're good. All right, Dave. We've got that target in the book. Do you want to have a go back to the slide deck, or do you want to carry on with a few more?
I think we've bored them to death regarding that issue.
Oh, the slide deck?
Yeah.
Oh, okay.
Yeah. You know, if anyone out there is interested in getting started in photometry or spectroscopy, you know, let us know. We can put you onto some good people to get you going down that road. I am totally a novice playing around with a very simple low resolution spectrograph, and Gary's doing some stuff with photometry. Science is a fun thing to do once you've looked at a lot of things in the sky and you want to understand more about it. So that's kind of cool. And we just wanted to introduce you to the concepts of a light curve in photometry and the spectral color observed in a spectroscope or spectrography. And if you go back a little bit and remember a little bit about that Hertzsprung-Russell diagram, the horizontal scale.
Did we actually show the diagram?
What?
Did we show the diagram?
I don't know that we did.
Okay. Well, I think we should at least show that, because that is actually an interesting diagram.
So Gary's going to show us the Hertzsprung-Russell diagram. Get that up.
Okay. So.
And it'll be coming here. So the Hertzsprung-Russell diagram is a really great tool. It's what we call a scatter plot, where we put things on a plot with two dimensions. And the scatter plot tells us something about the stars. Well, this is one way we classify stars. In fact, it's the key tool that everyone uses to get us started in the right direction on what a star is, where it is in its stage of life, and so forth. So the horizontal scale has to do with the color and the temperature of stars. The temperature affects the color of the stars. And on the diagram, you'll see on the left-hand side the temperature of 30,000 Kelvin, on the right-hand side about 3,000 Kelvin. And that would be the surface temperature of the star measured at the photosphere, and based on a spectroscopic analysis of the star. It's very basic stuff, very low-resolution job for a spectroscope. On the left-hand side, you see the vertical scale, which on this chart says absolute magnitude. It has to do with how bright something is, or luminosity. And Gary's playing a lot with luminosity right now. The bright things are at the top, and the dim things are at the bottom. Don't get confused by the numbers, because that's a magnitude scale which is inverted from being logical. So bright is on the top, and dim is at the bottom. And what you do is you measure the color of a star, its color temperature, and you measure its brightness, and you put it on this scatter plot. And you will see near the middle of the Hertzsprung-Russell diagram, we have the word sun, and that's where our star, our sun, is. It's around 6,000 Kelvin at the photosphere, and I can't quite read the magnitude scale, the absolute magnitude, whatever it is, 4, whatever it is.
Yeah, it's about 4 to 5.
So that's what you do. You measure the color temperature and its brightness. You get those numbers, you put it on this plot, and tells you a lot about the condition of the stars in general. Across the center of it, you'll see it looks like a river. We call that the main sequence. It's a horrible name for that term, because it indicates that a star is sequencing or moving along that path, when in fact it does not. But the main sequence is a lot of stars, a high probability that stars will end up somewhere on that path, somewhere on that area of the chart. So that's why we call it the main sequence. Above and below the main sequence are special stages of a star's life. For example, our sun, which is currently in the main sequence, will be moving upward towards the red giant phase.
Yeah, so our sun will go in this direction here. It will.
There you go.
Hold on, I got to make sure I'm on. Can they see my arrow here? I'm not sure. So if you can imagine a 45-degree line going, actually maybe a 60 degree, 60-degree line going from the sun kind of to the right hand side there. Some will move out of the main sequence at some point, probably around 4 to 4.5 billion years from now, and it will move into this into the area where you see the big red stars known as red giants. And if I can get a cursor working here, it would be really good, because I could show you a little bit. How do I get a cursor working? But so to a couple of points that Dave's made, on the y-axis there, that is absolute magnitude. That is not relative magnitude. What we see when we're looking up at the sky is relative magnitude of stars. So generally, the stars that are closer to us, you know, look brighter because they're closer to us, and the ones that are a long way away look fainter. But then there are, you know, differences associated with just the physics of the star and how brightly it's burning and stuff like that. But an absolute magnitude is measured if you from a standard distance, which I believe is 10 parsecs. And so that would be the magnitude of the star that you would see from a fixed distance of 10 parsecs. So that's absolute magnitude on the y-axis and temperature on the x. And the stars in the main sequence are related to each other by that river, if you like, that fit. And as Dave mentioned, the stars on the main sequence don't move. They don't move up or down the main sequence. They do move out of the main sequence. Stars that are generally cooler, like our sun, for instance, will move out of the main sequence, going right and up into the red giant phase. They will then become red giants for a while. They will then transition back from the red giant phase to the white dwarf phase, which is on the left lower side, and they will become white dwarfs, and eventually at some point the star will actually just cool down to the point it will stop fusing, fission will stop happening, and it will stop creating energy, and it will just cool down, and it will then drift back towards the cooler temperatures again in the white dwarf area. The stars that are high up on the main sequence in the blue area, these are the stars that will eventually move off to the large blue stars where you can see Deneb and stuff, and it's these class of stars that will actually end up doing some sort of nova at some point. And obviously the most spectacular of those would be a supernova. So it's the blue stars when they move out of the main sequence and they go up and to the right into this area that the sort of Deneb is in. That's when they're in danger of going through some sort of nova phase. So there is movement of the stars, not up the main sequence, but to the left, and then if they go into the red giant phase, back to the to the right, and then back to the left and low on the chart. If I had a cursor, I'd be able to show you that more clearly. Anyway,
we have two good examples. Actually, it is now about 9:52.
Okay.
How about this?
Yeah.
We could show the Eskimo Nebula,
okay,
which is a planetary, which gives us what an example of what a low mass star will end up.
Yes.
And then we could end up with M1.
Okay.
Which is a supernova remnant.
All right, sounds good to me.
And that would be the two extremes of, the end of a star's life.
Okay.
So the Eskimo Nebula is NGC 2392.
2392.
I think it's pretty high in the sky, so.
It is, yeah. Okay, I'm going to slew the scope onto that.
So while you're moving the scope,
okay.
A star is it's a ball of gas, and basically it's a fusion reactor. So it has layers. If we take our sun, for example, the outer layers have a lot of hydrogen gas, and as the hydrogen gas is compressed by gravity, it begins to fuse into helium. So helium is heavier than hydrogen, so the helium stays in the core, the center of the star, and it cycles light and heat back out. So you have this convection where hydrogen is sucked in by gravity. It is fused into helium, and it creates light and heat, which cycles back out and gives us nice light and heat to give us a summer afternoon here in San Diego, and makes life pleasant on this type of planet. So that's what's happening, very, very quick level. Larger stars, the helium builds up a lot of helium. There's enough gravity, enough helium. It begins to compress the helium. The helium begins to fuse into heavier elements like nitrogen, oxygen, whatever. And those layers continue to develop fusion layers that build heavier and heavier elements all the way down. Ultimately, if you have enough fuel and pressure, it might even begin to fuse iron in the core. Once it fuses iron in the core, the star can't do much more than that. So eventually, the hydrogen runs out. And when the hydrogen runs out, the fusion reaction stops, and there's not as much fusion pressure, outward pressure from the fusion reaction. So that layer begins to collapse. And if you have a large star, the helium fusion layer runs out of, you'll run out of helium because there's no more hydrogen to make new helium. So eventually this can cascade down into the core of the star, and the star collapses because of gravity, which on a supernova ignites a giant explosion that we call a supernova. On a smaller star like our sun, it doesn't cause that kind of an explosion. Rather, what it does, the fusion reaction stops. There's less outward pressure, and the core sort of collapses into a white dwarf, but there's not enough energy and mass to ignite a higher level, a nuclear explosion. So the gases around the outer layer of the star begin to expand because of the kinetic energy from all of that stuff going on, and the thermal pressure. It expands into the universe around the white dwarf and makes this beautiful cloud that we call, ironically, we call it a planetary nebula. And there are lots of planetary nebulas in the sky, and I think Gary's got one.
I do. We got
one here.
Pretty decent image here. So
the Eskimo.
So this is the Eskimo Nebula, and first of all, I'll show you with a field of view. My telescope field of view is about just over half a degree by half a degree, so you get an idea of the size here. It's a relatively small target. So I'm going to zoom in and reposition, and I think that gives you a pretty nice image there. You can actually see the gas layer, and you can see the central star. I'm going to try and see if I can get a little bit more. Oh, here we go. Let's just gonna move my sliders here and just see if I can get the image processing right to give us the best image. That looks quite nice. So yeah, so there we have a fairly nice rendition of the Eskimo planetary nebula. We can certainly see its central star, and you can see a couple of different shells in the gas nebula here. There's this fairly distinct inner shell, and then slightly more diffuse outer shell. And you can see this is expanding in the way that things expand naturally, which is a circle or a sphere, and in this case it's actually a sphere. Of course we don't see it in 3 dimensions, we only see it in 2, but you see this beautifully expanding gas shell coming out of the planetary nebula, and I can probably even zoom in a little bit more. And now we're getting down to like the pixel resolution of the camera. You can start to see the pixels now, the individual pixels on the camera. So I'll just drop back a tiny bit. But yeah, that's a fairly nice image of the Eskimo Nebula there, Dave.
Yeah, and that's what our star is going to look like in about 4 billion years.
Yeah, Joy's my daughter. She's 6. She was actually a little concerned today because she said to me, "Daddy," she said, um, "will our sun explode?" And I kind of went through the process of, well, it's going to expand and it will become, a red giant. And when it does that, the expanding gaseous cloud of the sun will envelop the inner planets. And she was very concerned about this because she was concerned about her hamster really. Uh, but I did reassure her that it wasn't going to happen for a few billion years, and that calmed her down a lot. But so yeah, she got the concept of the expanding sun and the size and how far it might come out. And I think I said to her that it would probably expand about as far past Mars, right? But it won't get to Jupiter. To kind of give you an idea of what we're
Probably
expecting in terms of the expansion of the sun
something like that. Yeah.
when this particular event takes place. All right, so I think we've got a nice image there of the Eskimo Nebula. So probably time for our last image of the
I
night.
think so. M1.
M1. Okay.
Yeah. So Gary's going to go over to M1. M1 is a supernova remnant, and
Okay.
it has a fantastic place in history. You may have heard one of our earlier uh, programs where we talked about the Messier objects, and this one, the story is wonderful because this is a supernova that was actually observed close to, our part of the galaxy um, by many civilizations in the year 1054 AD. So in 1054 AD, in the Chinese record, they said that a new star appeared in the sky and that the star was so bright it could be seen in the daytime, and it lasted for many weeks. Other cultures have also recorded seeing a new object in the sky in 1054 AD, and clearly there's confirmation from different locations around the world that this was actually a real event. And since then, of course, the general location of that star, that reporting of the new star in 1054, we have since found this supernova remnant that we call the Crab Nebula, and the history of that finding is pretty cool stuff. So you may have heard this. Let me run through it real quick while Gary's getting over there to M1.
Yeah, I'm there. I've just switched the guider on so that I can
Okay.
actually
Okay.
take some longer subs. And the guider started working again, which was good news. So I'm going to clear my stack.
So after the recording by the Chinese and others in 1054, there was not much history about this particular object. And then in 1682, Edmund Halley was a comet observer, and he observed a comet, and he was thinking a lot about comets and so forth. He was trying to track the comets, figure out their orbital uh, path and so forth. And he came up with the concept that this comet he found had a path that he could or an orbit that he could actually calculate, and he predicted that that comet would return as a periodic comet in the year 1759. So this is 1682. He predicted that the comet would return in 1759, and that was a very interesting concept because no one had really thought about comets being periodic or returning. They were just something you saw in the sky, and they didn't realize that they could actually be in an orbit that they would come back. So interesting thing, Edmund Halley. You've heard of Halley's Comet, right? So this is where the story goes. He predicted the comet would return in 1759. So in sometime about that, as you're getting to the mid 18th century, there were other people thinking about this comet and Edmund Halley's prediction that it would return. And I'm not sure who did the computation, but there were computation done by other astronomers who actually predicted that 1759 was wrong. It's going to return in 1758. And so they adjusted their timings, and now all of the comet hunters, including Messier and the others, are looking for this comet in the year 1758. So as they're searching for the comet, they predicted that Halley's Comet would return somewhere in the constellation of Taurus, and so they're looking for it, looking very carefully for it. Now they have better instruments in 1758. And Messier, among a couple others, while looking for the comet, discovered this thing here, this big blob that Gary now has up on the screen. And they originally thought that they had found the comet. So that's great, except that by watching it for a while, they realized this particular blob that they thought was a comet is not moving relative to the background stars, so it cannot possibly be a comet. But in the course of finding something that was not a comet, Messier began his list of items that are not comets, known as the Messier list, with this object here called M1, which in fact was the discovery of the remnants of the supernova explosion from 1054. And we've since, later computations of the location of the sky has pretty much confirmed that this is a good approximation of that location that was reported by the Chinese astronomers in 1054. So now we actually have a human eye observing a supernova in 1054, and here we are in the year 2021 observing the remnants of that explosion as this big cloud of gas known as the Crab Nebula. So that's the history. It's about 6,000 light years from here in distance, and it's a beautiful object. Sometimes you'll find some images that are really enhanced that make this thing look really colorful and fantastic.
Yeah, there's a lot of detail in this image if you can get it on the right night. Unfortunately, I don't think we're going to see a huge amount of that detail this evening. I've got about 4 minutes of imaging already in the stack, and it's a little on the fuzzy side for a variety of reasons. But we will at least get to see the supernova nova remnant here, albeit that I don't think we're going to get a huge amount of detail. But it's beginning to form reasonably well. Again, just to give you an idea of relative size, that is the full field of view of my telescope. So the moon would just about fit in that field of view. In fact, it would fit with a little bit of black on either side. So if I now zoom in at 50%, you can see the image of M1 in a little more detail. And as this forms and the noise drops out of the picture, you actually see a number of lanes or filaments, probably is the best word, running through the Crab Nebula, and it actually is a really spectacular object. So if you are interested, take a look online. There are some absolutely fabulous images. It's one of the favorite targets of our astro friends in the club, and of course they will have imaged it somewhat higher in the sky. We are catching it very late, which kind of brings us to our theme, right, really, of the fact of winter disappearing, and we're now heading into the more summer skies.
It is time to say goodbye to winter.
Yes.
And I think our next event should look at some new spring objects in the eastern sky.
Yeah, we're going to be doing a couple of different events coming up. So please subscribe to the SDAA YouTube channel for updates. We'll certainly be doing another session where we'll be looking at some new objects rising in the eastern sky. So we'll be getting ready for the summer objects. Now is galaxy season, and as we sign off here, I can say if you've not watched any of Mike Jerry's YouTube stuff, go onto Mike Jerry's YouTube site and catch him. He'll probably be imaging for about another hour, I'm guessing. He was kind enough not to directly overlap with us tonight, and so he joined us for the first hour, but I know he's now imaging from Bortle 2 skies in Death Valley, and he shoots some absolutely fabulous galaxy images. He'll be shooting in black and white tonight, so if you get the opportunity and you're up for a little bit more EAA live streaming, go to his YouTube channel. If you can't find it, just go on to Cloudy Nights, go into the EAA forum and live stream announcements board, and if you go to the last posting, that's Mike's YouTube link for tonight's broadcast probably. So if you fancy a little bit more time looking at the night sky, please check out Mike. And the other thing that I'm certainly trying to get to at some point is an exoplanet live stream. This is going to be a bit of a challenge, but I am actually hoping that we can either do a variable star live stream. Will be fairly straightforward because the magnitude change is fairly significant, but I'm going to try an exoplanet live stream, and that is to actually see what we believe to be a planet transiting in front of a distant star. It's going to be It's not a quick event. It will take a couple of hours, but if you're actually interested in seeing a star or a planet of another orbiting another star transit across the front of that star, I'll probably be trying to do that later in the year, and I'm trying to do the prep work for that now. So let me go back to my slide deck, and we'll just go to our back slide here. So we have a YouTube channel, as I mentioned, and you're obviously watching this evening. We're also on Facebook. Please like us on Facebook, and we have a new website where you can view a number of things about the club and look at some of the presentations that the club has had recently. We've also got some interesting other stuff up there that makes a good read. So if you want to know a little bit more about the SDAA, please take a look at our website as well. And we've had a few of our colleagues out here. Woody has been behind us for most of the night here. We're all getting a little chilly. He's wrapped up in a blanket. So thanks for Woody coming along. Jose has brought his big, incredible pair of binoculars with bino eyepieces on. He's been doing a little bit of visual observing from this dark sky site, and Dennis is in the distance because I can just about see him in the distance, illuminated by the light coming from his iPad. So Dennis has been listening along as well. So it's been great to have a few colleagues out here this evening, and I'll just hand it over to Dave for a few final words.
So thank you very much for joining us for this San Diego Astronomy Association outreach event, and we hope to continue doing these virtual events even when we are able to restore in-person, hands-on at the eyepiece traditional star party events. When we do, I suspect that will occur here at OakOasis County Park or County Preserve. A big shout out to the County of San Diego and to Ranger Kyle for supporting us and giving us a location that works very well for us. We have a nice clean parking lot, we have power, we have a clear dark sky with a very nice horizon, and we have great internet connection here. So it's working well, and we very much appreciate Kyle, you, and the county for supporting us in this event. Anyway, with that, I guess we'll say goodnight and look forward to our next event. We're always open to comments by way of email. You can reach me at the outreach at SDAA.org. That's outreach at SDAA.org. And or go to the San Diego Astronomy Association website and look for contacts, and you'll find what the outreach program is doing, and send me email when you have questions or comments or whatever. So, Gary, I'm sorry that you were not able to recall the either Bob Dylan song or uh, you know, the times they are a changing.
Well, I remember Bob Dylan. I mean, for sure. But when you went back to the age of Aquarius,
Oh
I mean,
yes,
that
the
was
Age of
just
Aquarius.
way before my time. You
The
know.
funny, the funny thing is, I've heard that song. I know about the song. I know about the musical. It did not dawn on me what the term "the Age of Aquarius" meant
No.
until now. I realize the precession of the vernal equinox eventually puts the vernal equinox into the constellation of Aquarius.
Although
And
somehow I think the
yeah,
songwriter did not have that in mind when they wrote the song.
yeah,
Anyway, guys, it's been fun. We've had a good evening. I hope you've enjoyed it. Sorry for the technical problems at the beginning, but you know, there's a lot of gear, and sometimes things just don't work out as you plan. So, happy Easter, everybody,
yep.
and we'll look forward to catching up with you again on another live stream, hopefully in about 3 to 4 weeks' time.
Okay.
Good
Good night,
night.
everyone.